Good morning, everybody. I will show you some results of our recent studies of ice wedge thermokarst in northern Alaska. I think this topic is really important, first of all, because wedge ice is the most common type of massive ground ice, and we have ice wedges practically everywhere in northern Alaska, and degradation of ice wedges has a very strong impact on both environment and infrastructure. There are two main types of ice wedge polygons. In reality, it's a little bit more complicated, but just for simplicity, let's consider low-centered polygons and high-centered polygons. Low-centered polygons indicate growing active ice wedges, and they're typical mainly of recently exposed surfaces like floodplains and soil lake basins, while high-centered polygons indicate partial degradation of ice wedges, and we can see them mostly in the areas with older deposits like old drain lake basins and primary surface of the Arctic coastal plain. Size of polygons typically varies from 10 to 20 meters across, and typical ice wedges in the coastal area of northern Alaska from 1 to 5 meters in width, and up to 3, 4, sometimes 5 meters in depth. But just further south, in the area closer to the Arctic foothills, we have a different situation. We have syngenetic permafrost named Yedama, so with a thickness of deposits sometimes more than 30, 40 meters, and we have huge syngenetic ice wedges there, whose dimensions can be really large. Such ice wedges can be up to 10 meters in width, and the vertical extent can be more than 30 meters. And unfortunately, we have this kind of permafrost in Point Lay. It's not 30 meters, but 10 meters is also more than enough, and more likely we have at least 50% of the volume of the upper permafrost consists of wedge ice. When we study ice wedges, of course, we prefer to study natural exposures, riverbank exposures, and coastal exposures. But when we need to work in other areas, the only way to study ice wedges to figure out the size and the shape, drilling holes. You can see examples of cross sections of ice wedges here in the Utqiagvik study area, and some in the old surface, some wedges here are really big, sometimes 7, 8 meters in width. They can penetrate up to 4 meters in depth. More likely, Yuri Shur was the first who approximately 20 years ago noticed that something is going on, especially in northern Alaska. Ice wedges started degrading at the alarming rate, and evidence of degrading ice wedges could be found almost everywhere. And after that, you can see there are dozens and dozens of publications, lots of observations of widespread ice wedge thermokarst everywhere in Siberia, in northern Canada, of course, in Alaska. These are just several examples of degrading ice wedges northern Alaska, mostly in the coastal area. That's what we can see from the plane, helicopter, or if we look at the Google Earth image. Degrading ice wedges everywhere, lots of water-filled troughs and ponds, and it looks really scary. And definitely it creates lots of environmental and engineering problems. And the biggest question, what will happen next if these degrading ice wedges will turn into something much bigger, like formation of large and deep thermokarst lakes? Would it lead to complete degradation of ice wedges? And in 2006, Yuri and Tor Jorgensen, they published a paper which showed that in many cases, this process is reversible. So they showed 4 main stages of ice wedge evolution. First, after increase in the active layer thickness, we have initial degradation when the wedge is affected by seasonal thaw. But after a while, this initial trough is filled with water, and snow creates additional positive feedback, and ice wedge degrades deeper. But then stage D, this water-filled trough is filled with sediment, with organic matter, and it leads to stabilization of ice wedge, decrease in the active layer thickness. So after a while, most of wedges become relatively stable, and the growth continues. This is a last version of the same conceptual model. It's rather complicated, and of course I don't have time to describe all these stages. The degradational stages are in the left column, but the main idea of this model is that ice wedge degradation can be interrupted and reversed at any degradational stage, and eventually, after several years or several decades or even several centuries, depending on the scale of degradation, the surface will return to almost the same condition with new ice wedges, and of course it will not be exactly the same as we could see before degradation. So we call this process quasi-cyclic. We developed kind of a method of estimation of vulnerability of ice wedges to thermokarst. It's based on measuring the thickness of soil layers above ice wedges. Again, it looks maybe complicated, but actually it's rather simple, because for example, if in August or September you drill a borehole above the ice wedge, and you see that below the unfrozen active layer, you can immediately encounter wedge ice, or if this wedge ice is protected by a very thin layer of frozen soil, 1 or 2 centimeters, that means that this ice wedge is either currently degrading, or it's very poorly protected and it's extremely vulnerable. And for example, in the next summer, so depth will be deeper, this wedge definitely will be degrading. And opposite, if you see about 20-30 centimeters thick layer of frozen soil above wedge ice, that means that it's relatively well protected, and we hardly can expect its degradation in the nearest future. several examples. So here it's from Pruda Bay. You can see degrading ice wedges, water depth about 50 centimeters, active layer thickness also about 50 centimeters. And at that time, this wedge was degrading. Another example of advanced stabilization of the ice wedge. On the old air photos, we could see a rather big thermokarst pond here. But when we drilled at this site in 2012, we found that first of all, you see there is no pond here anymore. And the wedge ice was encountered at a very significant depth, 1 meter 20 centimeters. And here we have about 70 centimeters thick layer of ice-rich soil. You can see the core at the bottom of this slide, rather ice-rich soil, what we call intermediate layer. And it protects this ice wedge perfectly well. So no more degradation for this wedge until new ice wedge developed at this place. So will be close to the surface, but it will take probably hundreds of years. Thank you. And we all can see very dramatic changes when we study historical imagery. This is another example from Pruda Bay. Here you can see old and very stable ponds, almost no changes since 1960s. But at the same time, you see a huge increase in the area of water-filled troughs. Yeah, of course, it looks scary, but when we started pouring in these ponds, it looks like that most of them now are completely stable. For example, this deep pond, water depth more than half a meter, but here we have more than, yeah, and you see it's September, it's maximum. So here we already have more than 20 centimeters of ice-rich frozen soil, which perfectly protects this wedge from further thawing. And probably the biggest factor is accumulation of organic matter, growth of aquatic vegetation, and it occurs very fast. And it results in a dramatic decrease in the soil depth. Totally, we drilled hundreds and hundreds of boreholes in various study areas. Our main study area is Pruda Bay, but we also have transect in Utqiagvik, Jaga River, Itkilik River, Anaktuvik River fire area. And after our initial studies, several years after that, we decided to re-drill some of these locations. And it looks like that practically all ice wedges which were degrading 7, 8, 10 years ago, all of them are stable. At the same time, we could see some ice wedges which are degrading now. So the data from Pruda Bay, where we re-drilled 52 locations. And you can see only 14 of ice wedges are degrading now. And many other ice wedges, they experience stabilization, or we could detect some degradation, but now these wedges are already and this is one example from our Utqiagvik study site. Process of degradation and stabilization can go really fast. You see dry trough in the image of 2010, but in 2012, it was already a pretty big pond. And, ice wedge was practically exposed. We could feel it walking there. It was a huge 2 meters deep erosional niche, and we expected that at least here we have a perfect storm. Definitely it will develop into something much bigger. We will see a big thermokarst pond, but nothing happened when we came here in 2015. It already looked stable. And you can compare images 2015, 2022, exactly the same. And last summer I drilled here, and the ice wedge was already pretty deep, so more likely this site will be rather stable. So definitely I don't have time for conclusions, but the main point is that at least for this area, for North Alaska, for area with cold continuous permafrost, under current climatic conditions, we hardly can expect formation of new thermokarst lakes, and hardly can expect complete melting of ice wedges. It might be a different story in other regions, for example, Sierra Peninsula, where just warmer climate. So probably that's what wait us here, but after a while. Thank you.
Thank you. Are there any, oh, there are questions for you. Jen?
What is critical in the process of this stabilization of the ice wedges? Is it the fact that peat starts building up on top of them? And if you didn't have that, would you expect thaw to continue?
Yes, you are right. So surprisingly, Vladimir showed us the day before yesterday example from the high Arctic, from Canada, really fast degrading ice wedges, but we cannot expect in that climate fast formation of moss and peat. So more likely degradation can be more dramatic in such areas. But here, you can just look around this building. You can see lots of fresh, bright green moss in all these ice wedge troughs. These wedges they were degrading several years ago. Now more likely they're stable.
I have a comment.
Okay.
You should probably know so
Of course, I know you have a different opinion.
The key, and we don't have this 100 years to restore.
Yeah. Sorry.
We will see.
Yeah, it could be in 40 years, it could become perfect. And in Fairbanks, you know, ice wedge is not growing.
I'm talking about what is going on now, and we compare what we could see 10 years ago and now.
If you trust the climate models, if you're not, that's perfect. That's okay.
I'm not talking about climate models.
Okay, back to your corners. So Misha, this is a two-part question. First, obviously, the intermediate layer is a buffer. Obviously, you found that to be a great buffer for the development of ice wedges. So is there some way to detect from vegetation or surface features a prevalence of about a thicker intermediate layer versus a thinner or non-existent intermediate layer? And then the second part of my question is what exists at Point Lay? Is it a very extensive intermediate layer, or is it just moderate or non-existent? Thanks.
Of course, we have a feeling where we may expect well-developed intermediate layer. For example, in these water-filled troughs, if you see thick floating organic mat, more likely so depth is twice smaller than it was before. So we checked it many times. Yes, that's the second question.
Repeat the question. Repeat the question.
Yuli's question.
Yeah, I will talk about this. But of course, if we do want to know for sure, we should core take a look. But now totally we have many hundreds of these short boreholes. One day I should calculate how many, probably 500, I don't know. And so of course we have some feeling. The second question, what we have point lay looks like it's exactly the same what we could see in other areas like our Itkillik site. You go there. So we have a pretty thick intermediate layer above large Yedema wedges with much smaller modern wedges, very well developed ataxitic crust structure typical of the intermediate layer. That's what we could see. Excess ice content average about 40–50% for point lay. And in undisturbed areas, we mostly can see degradation of these upper ice wedges plus smaller ice wedges. But in developed areas, unfortunately, large Yedem ice wedges are already melting, and that creates lots of problems.